Hey there. Today, let's try to solve this problem called count stable subarray. So in this problem, you are given an integer array nums. A subarray of nums is called stable if it contains no inversion, i.e. there's no pair of indexes where I less than j such that nums I is greater than nums j. So basically there's no inversion within the subarray. You are also given 2D integer array queries of length q, where each queries LR will represent a query. For each query, LR compute a number of stable subarray that lie entirely within the segment nums L and R. And finally, return integer array answer of length q, where answer I is the answer of that query on the ith index. And note, a single element subarray is considered stable. Yeah, because a single element has no inversion that could happen. So let's look at the first example. Nums is 312 and query is 0, 1, and then 1, 2, and then 0, 2. Let's take a look at this example first. Okay, let me paste here. So this is the array and this is the query. And now if we look at 0, 1, it represents the subarray here, which is so the first query is looking at 3, 1. So you can see if we only look at stable subarray, so only 3, this 3 is a stable subarray, and this 1 is also a stable subarray. But this 3, 1 is not a stable subarray because it contains this inversion pair. 3 is appearing before 1, but at the same time it is strictly greater than 1. So this subarray doesn't work. So there are only 2. So that's why the answer 0 will equal to 2. And for second query, second query will be 1 and 2. And you can see the stable subarray here. Well, it can be 1, obviously. Actually, every single element will be stable subarray as we saw in the problem description. But this time, the combined, the whole subarray itself is also stable because you can see this is non-decreasing. So answer 1, the second element will be, you can see there's 3 subarray that are stable, so you just 3. And then final, the third query is 0 and 2. So the stable subarray here, again, 3, 1, actually 1, 2, 1, 2. This is 0, 2, which represent 3, 1, 2, the whole array. So the stable subarray can be 3, can be 1, can be 2. And then we just look for every subarray now. So this 3, 1, this is a subarray from this range. But this 3, 1 is not stable because, again, 3 and 1 kind of violate the rule. So we cross them out. And then we go 1, 2. 1, 2 works because it's non-decreasing. And we 3, 1, 2, the whole array itself can be a subarray. But again, because this violates the inversion rule. So this 312 does not count as well. So in total, they're like 3. Answer 2 equals 4. And then that's why we have to answer this array 3 to 4. Yeah, that's pretty much all for the problem description. And let's think about how can we actually solve this problem. Okay, so actually this problem is quite difficult. So instead of just solving the whole subarray range query problem right off the bat, we can try to solve a simpler version of the problem first. Okay, let's look at this problem. dpi will be equal to the number of stable subarray ending at index I. So to solve this problem is significantly easier than the original problem, but is still somehow related. Let's think about how can we solve this subproblem first. So if we're looking at dp0 is always going to be 1, no? Because, well, it's ending at index 0, and the number of stable subarray is just the one that is starting at 0 as well. So it's the only element the first element basically. And for dpi, well, this is a little bit more tricky, but it's still very straightforward. We need to know the previous element, right? So let's assume that we know dpi minus 1. This means all the stable subarray ending at I minus 1. In what situation can we reuse this? Right? The answer is that if we are greater than the previous element or equal, if we are greater or equal to the previous element, then we can just use it. All right? And we need to plus 1 because this nums I itself will be the only element, the only nums I element can be a subarray itself, so we need to plus 1. And all the previous subarray that is stable, and we just reuse them. The count, we just reuse them. For example, previously we have like 2, 3, 4, 5, I don't know. This will be like maybe 2, 3, maybe 1, 2, and then now the nums I is like 10, and then we can just do it, right? We can just because this 10, we can just add this 10 to every valid stable subarray before, and it will also make it stable because of this property, right? Nums I is greater or equal than the previous element. Yeah, that's the idea. And if it is not, then, for example, in the example here, 312, we're looking at 1. If it is not greater or equal to the previous element, then we just start straight from 1. So there's only one subarray here. So it will be just 1, the only element itself. That it will be the recursion step. Now we already solved this problem, and how are we gonna use this to help finding the range? Well, we can think of using the prefix, right? Because if we do prefixed, it will just be the sum of dp0 all the way to I. And this is just prefix sum. And if we do query, it will be like LL, that will be just prefixed allo minus prefixed L minus 1. And this will give us, you know, the description for this will be the number of stable subarray ending between L ... But some of you might already notice we are overcounting something. well, specifically, this is very close to what we need, but we're still overcounting something. So obviously we don't want any subarray ending before L and also after L. So this is a good first step, but there could be a way where the subarray starting before L, but ending on or after L. Maybe I just change it to this. This will look better. L after L, but before L. So this kind of subarray is overcounted in this query. So that's why we need to basically tweak a little bit of our left pointer. Okay, that might be a little bit abstract, but just take a look at the example. So 7, 3, 4, 5, 8, 9, 10, 3, 1. So this is numst with this. And let's assume we have a query where L will be 5. This is L, and then we want to end in this index. So basically we are looking at this. So why I said the query LR wouldn't work is because look at this definition of this. It is the number of stable subarray ending between L and R. So the problem is, well, this subarray 4, 5, 8, 9, this array will also be counted. See, because this is actually ending here, and this array is also counted 4, 5, 8, and these are overcounted, and we don't want that. And obviously this 5, 8 and this 8, 9 are counted correctly, and it's fine to count it. But this other thing that is crossing the L pointer, I mean, delete that. This is the L pointer. I don't know why I keep doing that. This is the L pointer. So anything crossing the L pointer, as you can see, will give us like the overcount. But what about this one? 7, 3, 4, 5. Would this be overcounted? No, because it won't be counted in the first place because this thing is not stable. So when you look at the example, you can see there's some interesting property. So there's actually here 3 and 4, and also so basically this 3 and 4 you can choose. For example, I want to over counted stable subarray. So it can actually start from 3 and 4. You can start from anything actually. J all the way to L minus 1, as long as numst J dot L minus 1 is non-decreasing. So this is the starting point. Let me do that. Starting point. So this we are concerning the overcounted stable subarray. So the starting point can be j and l minus 1, as long as nums j and l minus 1 is non-decreasing. Because imagine you pick this, and you can also pick anything here. So for the ending point, it can be L. It cannot be n minus 1, because if it is ending at L minus 1, it does not cross L. So like we want to know anything that is crossing L, but at the same time is stable, because this thing will be overcounted in our original query LR, which is the prefix sum that we did. So now back to the ending point of the overcounted stable subarray. So it can end at L, and it can also end at J, as long as nums L dot J is non-decreasing. So I hope you see the pattern here. So you can choose any starting point, and you can choose any ending point here, and they will form a stable subarray that is overcounted. So that's why the real answer for the current query will be query LR minus let's say the length of this one, JL minus 1 times the length of this interval again, LJ, and this will be the answer of the current query. So length of something LR is just R minus L plus 1. See? Okay. Now, the second question, which is not very trivial, is how do we know how many elements can we tweak? So we don't want to keep going. So for example, this 5, how many elements can we go that is still remain like non-decreasing? So in here you can go 5, you can go 4, you can go 3. So basically we want some data structure that can tell, for example, if I ending at this index, what are the possible starting point on the left that can still remain non-decreasing. So basically just the non-decreasing subarray ending at any index. And it also needs dp start, which will be used to find the possible ending point where like if I start at this index, then what elements can I reach? So in this case, I can end it here, I can end it here, I can end it here, but I cannot end it here because this is no longer sorted or non-decreasing, so on and so forth. So let me write down. We need dp end I. So this will tell us the non-decreasing subarray length ending at index I. And we also need dp start I, where it stands for the non-decreasing subarray length starting at index I. So once we have that, and we can make this so much faster than just doing the for loop. Right now we are just looping. We don't quite know what the j is, but once we have that, this dpn, then we can just use, so this is just also equal to dp and L. And this one will also equal to dp start L, I think. So the starting point can be L, the ending point has to be non-decreasing, but so this dvn L minus 1 because it cannot actually start at the index L, but it also has to be non-decreasing. So here, what I'm saying is that you cannot end at 5 because that will be the same element. We need to be crossing. So you need to start as late as L minus 1, but we cannot do dpn L minus 1 because if we do L minus 1, this can be just 7, and if that's the case, we should return just 0. I hope that makes sense. So that's why we need the dpn L minus 1. And then we know the possible starting point, and the dp start is basically this one. So how many numbers here can we choose? How many ending points we can choose? So this thing, and we also take the minimum as well, because this dp start L cannot be larger than the length, the array length. So this all minus L plus 1. So let's just make it as X, and let's just assign it to Y. And then once we have that, we can just do like X and then Y. Let me clear out that. Okay. So this is the answer, and all the thing can be done in O1. Yeah. And yeah, that's pretty much all for the intuition. There's some minor details on how to implement this dpn, which I will be explained in the code implementation, but it's not something crazy. It's quite straightforward as well, but the general idea is just like this. And as you can tell, the time complexity for this solution will be O(n), and the space complexity for this solution will be O(n) as well, because we use all these dp array, but we have multiple of them, but like we have constant, like maybe 3 times n, for example, it will still be n. So yeah, that's pretty much all for the intuition for this problem. Let's move on to the implementation. Okay, so first we're gonna initialize the dimension of the nums array and the query. Do n equals num dot size, and then m equals to query dot size. And then we have to initialize the dp array. So again, like dp I stands for number of stable subarray ending at index I, and we also need a prefixed long prefixed n, and so this prefixed I equals to number of stable subarray ending at or before index I. So basically it's just the dp sum from 0 to I. That's another way to describe that. So let me give myself more room here. Okay, and then we also need int dp start n, and this is dp start I means the non-decreasing subarray length starting at index I. Again, we will use this dp start to help us find what are the ending option for the subarray that is crossing L. Similarly, we also need dpn. Dpn I equals to non-decreasing subarray length ending at index I. Okay, so initially dp 0 and also dp start n-1 and also dp end 0, they are all equal to 1 as the base case, and prefixed 0 will be equal to dp 0, and then for I equals to second element all the way up to the end plus, and dpi, it depends on whether current value is larger or equals to the previous value. If it is, then all the previous endings of array I can also end with the current num_i. So that's why we can do num_i -1 plus 1. Otherwise, we just cannot inherit anything. So you just have to start fresh as 1, which is the only element, which is also the num_i. And prefixed I will just be the sum of everything. So it's just prefixed I-1 plus dpi. And dpn is going to be very similar because we want to know the non-decreasing subarray ending at index I. So we in this case we also need to know if it is larger or equal to the previous element. So if it is, then we can reuse the previous element. dp and I-1 plus 1 minus 1. So what I mean here is that so dp, so let's assume there's 2, 3, 4, 5, 6, 7, and then when we look at this element 5, and we need to check if what is the non-decreasing subarray ending at the previous element. So for example, we could have something like that. If we are looking at 3, it doesn't matter how many non-decreasing element we can go from here. As long as these 3 and 7 cannot be non-decreasing, we cannot attach the previous subarray to 3. So in this case, 3 will just be 1. But in here, for example, in 6, I can look at, okay, what is the, so I just need to check if I am greater or equal than the previous element, which is exactly what I did here. So if I am greater or equal to the previous element, it means that any non-decreasing subarray ending at that, I can kind of attach it. So it's just plus 1. So that's why we can do here, if it is greater or equal to the previous element, we can just use dpn -1 plus 1, and that's why we will do just 1. The same goes for dp start as well. Let me just do dp I and n-2 0 I minus. We're going reverse because well, if you think about it, when we do dp start, we want to know the non-decreasing subarray starting at index I. So So for example, we are looking at this 4, then, well, it doesn't help us what this dp value is. Instead, this dp value actually help us to know the current dp value. So that's why we need to know the +1 value here. So that's why if we want to know the +1 value, we need to start from the very end. That's why we are not doing the dp start in this first for loop. We're doing this in the second for loop, which is looping the array reversively. So dp start I equals to very similar to what we do here, but this time we're going to check for let's see what here. For example, if we're looking at this 5, in what scenario can we inherit this 6th? Well, it has to be less than or equals to nums I +1, right? So because, well, for example, in this 7, we will look at 3. It could be a lot. It could be a lot of element over there that we can do it non-decreasing. But as long as this 7 is not greater, it's not smaller or equal to the next element, we cannot just inherit. For example, we cannot just inherit it because this will always break. So that's why. Let me close this. Let me delete this first. Okay. So we just need to know if the current element is smaller or equal to the +1 element. If it is the case, then we can do dp start I +1 because we consider the current element now. Otherwise, we'll just only consider current element. And yeah, and after the dp values are populated, we can start calculating the actual answer. Let me cross out this command. And okay, so this will be our answer, long answer with a dimension of m. And we go from I equals 0, I less than m, I plus. So the left, which is also the starting point of the query, will be the first element of the query, and the r will be the right boundary of the query, which also will be the second element of the query. So long current. So current value is, so initially we just do like the prefix sum, right? We just need to know like all the number of stable subarray ending between L and R, but like we will handle the crossing case later. So we just do the simple case first. L equals, this is just prefix sum, prefixed L -1. So again, this is subarray, stable subarray. Ending between L dot R. So, but like the overcounting issue, that crossing L, we overcounting here still. So we need to handle the overcount. Handle stable subarray crossing L. So what stable subarray can cross L? What are the left start choices? So if L is equal to 0, that is 0. Otherwise, it will be dp and L -1. So let me try to do that. So left start. So left start, I mean the stable subarray that is overcounted. This left start can be nums j dot dot L -1. And as long as nums j dot dot L -1 is non-decreasing. Let me give myself more room here. Okay, I think, Okay, I don't think it can be done in one line. Anyway, just leave it as that. And then the left and choices will be the dp start L. And also we need to make sure that it is not larger than the current length. So this left n can be nums L.j as long as nums L.j is non-decreasing. And after we have the left start choices and the left end choices, well, basically any start choice can match with any end choice. That would form us a stable subarray that is crossing L, but at the same time it is stable. So basically, these are the subarray that we have overcounted here. Okay, so that's why we have to minus equal type on left start choices times left and choices, and answer I will be just current, and finally we just return current. That's pretty much it. Let me actually do it this way. I couldn't stand it. It's too ugly. Here, let me put a comment here. Let me put a comment here. Okay, is there any space here? No. Let me put an empty line here, an empty line here. Okay, so let me try to run the code. Okay, return curse not. We should return answer. It's a typo. Run again. Okay, let's try to submit. Okay, accepted. Thanks so much for watching, and I will see you in the next video.